Hey guys, in today's video we're going to be learning all about multimeters. Now multimeters come in all different shapes, colours and sizes and have various buttons and different symbols, which can be a little daunting and confusing at first. But don't worry, in this video I'm going to be simplifying that for you. And actually there are only three main types of multimeter on the market, which are... So on the left here we've got the auto ranging multimeter, in the middle we've got the analog multimeter, and on the far right here we've got the manual ranging multimeter. Now the analog multimeters, the one in the middle here, barely get used anymore. To be honest, they kind of suck. They're obsolete, they're outdated, and there's far better options on the market now. For that reason, let's burn that one off and take a look at the other two. So you have the auto range multimeter, where you just select the feature that you want and it'll automatically find the range and value for you. Then you have the manual ranging multimeter, where you have to select a predetermined value, and then that will then allow you to take the measurement. I'll go into more detail with this later on in the video. Let's go ahead now and take a look at the auto ranging multimeter first.
So let's do a quick overview on some of the features you might find on a multimeter. First option is AC voltage, followed by direct voltage. Voltage is basically the pressure that pushes a current around a circuit. Then you have the millivolt symbol, which you can test on AC or DC circuits. The next feature has multiple options, which I'll cover now. First symbol is a diode check symbol, which allows you to test LEDs and diodes. Next you have the continuity feature, which allows you to check you've got a complete circuit. You then have the capacitance symbol, which ensures your capacitor is working properly, followed by the ohm symbol, which allows you to measure resistance in a circuit. You then have hertz or frequency, which tells you how many times a second the current changes direction. We then have the ampere symbol, which allows you to measure AC or DC current. Then you have milliamps, which allows you to measure smaller quantities. Then you have an even smaller scale to measure microamps. And you then have the temperature symbol, which allows you to measure air temperature as well as surface temperature. Let's take a look at the buttons now on the multimeter. Sometimes there's more than one feature, and the select or shift button allows you to cycle through these features. The hold button allows you to freeze the display for later reference. The range button allows you to change the unit of measurement. The relative mode button stores the existing reading and resets the display to 0. The hertz button tells you how many cycles per second. The min-max feature will temporarily hold the highest and lowest signal levels measured by the meter. Let's take a look at the inputs at the bottom of the multimeter. The terminal on the right is a general input for most features except measuring current. Your black lead goes into the COM port, which is a grounding or neutral terminal. The central red port is for testing current up to 600 milliamps. And for testing current up to 10 amps, you want the port on the far left of the multimeter. And at the top of the screen there, I've included a units table just to help you identify the values of some of these symbols. Okay, so that was just a quick overview of some of the features you'll find on a multimeter. Let's take a look at some of these features in a little more detail now.
Okay guys, so the first mode I'm going to be showing you today is the direct voltage mode, as displayed by the symbol there. What I'll do is I'll do it on the manual ranging multimeter. You have a choice. That's the auto range, that's the manual range. This one's slightly more involved, so I'll just show you how to do it on the manual ranging multimeter. So what you do is you'll take a look at the direct voltage symbol, again just there, and we have a selection of different values on the left. So we have to turn our selector dial to the correct value, and that's going to be determined by the voltage of these batteries. So we've got a 1.5 volt battery with the AA, a 9 volt battery, and then my Milwaukee battery is 18 volts. So if we were to test the 1.5 volt AA battery, you'd come over to your selector dial and you have to select the correct value. So it's above 0.2 volts but below 2 volts. So you twist your selector dial onto this value. The second battery is 9 volts. So if we take a look, 9 volts is above 2 volts but below 20. So we twist our dial to this value. And then the third option is the 18 volt battery. Well, again, it's above 2 volts but below 20, so the dial is in the correct place. Okay, let's go ahead and take a measurement of these batteries now, and remember to have the black probe in the COM terminal and the red probe in the multifunctional terminal. So, like I say, we find our value above 0.2 and below 2 volts for the 1.5 volt battery. and then you just test it over the anode and the cathode. We've got 1.6 volts. Then with the 9-volt battery, it's above 2 volts but below 20, so we turn it up one. And we have 8.93 volts. If you have a minus sign, you just switch your leads around, and there you go. And then the third battery is our 18-volt battery, and we have 19.47 volts. So what do you do though if you don't know the voltage value of the component you're testing? Well, that's quite easy. All you do is get your test probes and pop them across the anode and the cathode of the battery in this example. Then get your multimeter and get your selector switch and twist it one by one until you find a 1. Once you find the 1, notch it up 1 notch, and there you go, you've got your value, 19.47 volts. Let me give you another example now of why this mode is useful. I've set up an application with a few circuits on a breadboard, and I'll show you that now. So the direct voltage setting is very good at measuring the voltage drop of components and circuits. So on the left side here I've got a parallel circuit, and on the right side here I've got a series circuit, and I'll pop a picture on the right hand side of the screen just to make that clearer. So if we take a look at the voltage drop of this resistor, I've got almost 6 volts, and on the series circuit, if we do the same, approximately 3 volts.
As you can see from some of the examples I've just laid out, there's many applications where you can take a measurement using the direct voltage setting, such as batteries, most electronic devices are DC, you have solar panels and various other applications.
And just remember, when you are measuring or taking a measurement such as this battery, you want to measure between the anode and the cathode, as there is a pressure difference or potential difference between the two. If you're to measure at the same point, there's no potential difference, and therefore you won't get a reading. Now that we've taken a look at DC voltage, let's go ahead and take a look at AC voltage.
So the main difference between AC current and DC current is the direction it travels. Let's switch on the direct current circuit. With DC current, the electrons flow in one direction, as displayed on the right hand side of the screen. Let's turn off the DC current and turn on the AC current. Whereas AC current flows backwards and forwards multiple times a second, as shown on the left hand side of the screen. Here in the UK that's 50 times a second, over in the US it's 60 times a second, and the frequency is abbreviated in Hertz. And so if we take a look at these two oscilloscopes, the oscilloscope on the left shows an AC waveform as it's measuring AC current, as indicated by the arrow, which is why we use the wavy line symbol on the multimeter. And then on the right oscilloscope measuring the DC current, you have a straight line on the oscilloscope, indicated by the arrow, and that is why your symbol on your multimeter also illustrates a straight line.
Okay guys, let's go ahead now and test the voltage of this socket circuit. It's worth mentioning we're not playing around now with a few volts of electricity. This is 240 volts, and it will vary from country to country, but you are going to be measuring high voltage, so we want to be as safe as possible. So first things first, we're going to do a safety check on our test probes and make sure there's no tears or rips or anything like that anywhere down them. If there is, don't take the measurement, go out and buy some new test leads. It's not worth taking the risk. Secondly, when you're taking the measurement, make sure your fingers are behind the actual guard of the test probes. You don't want them up here, you don't want them anywhere near the metal, so make sure your fingers are well away from the metal. Okay. Once you've done your safety checks, you can then go ahead and twist your dial over to the voltage symbol with the AC sign. We then get our red test lead, and what we need to do is release the safety guard on the bottom 2 holes. The way in which we do that is you get your test lead and you pull it down like so, and that will release the guard at the bottom. You can then go ahead and put your black test lead in the bottom left like so, and then you get your red test lead and you pop your red test lead in the bottom right, like that. Make sure you always put your black lead in first, followed by the red lead. Once you've done that, you can then go ahead and proceed to turn on your socket, and we've got a measurement right there of 244 volts. Now that's one way to take the measurement. I far prefer using one of these socket testers. So this is a lot easier to use, it's safer. You just simply plug it in and it will measure and test your circuit wiring for you. Some of these even come with a display, so you get like a voltage symbol on the front there, so it will give you the voltage as well. And I recommend for this particular application using one of these socket testers over the use of a multimeter. Okay guys, the next feature we'll be looking at is the horseshoe symbol there, which is ohms for resistance. And what you do is you use your selector dial to select the feature. This has a couple of features on this mode, so we'll use the yellow select button to cycle through. At the moment it's on the ohms. If I cycle through, just to give you an example, we've got continuity, the check diode feature, we've got capacitance, and then back to the ohms. And then what you do is use your range to change the value. So at the minute we've got an M for million. Let's say we want to put it in the thousands range. We just cycle through our settings until we find our K. And now we've got thousands. So what exactly is resistance? Well, resistance is how difficult it is for the electrons to pass through a material. So if you have a piece of metal, for example, the electrons can flow nice and easily. If you have, say, a resistor, it's going to be more difficult for those electrons to flow, depending on the value of the resistor. So the higher the number, the more difficult it will be for the electrons to flow. And if you have something like a piece of rubber, for example, it's going to be very difficult for those electrons to flow. The reason for this is to do with the electrons and atoms within a material. So with things like copper, you have lots of free electrons that can flow easily, and metals generally are good conductors of electricity, whereas things like rubber, there's very little free electrons to flow, so the electricity struggles to flow through the material. And this is precisely the reason why we use rubber to insulate our copper conductors. So we've got some twin in earth there, some flex and some single core. And if I just give you a better illustration here, you can see you've got a copper conductor on the inside and then your insulation guarding it on the outside. Okay, so let's go ahead now and take a measurement of resistance. So as you can see, I've got the selector dial on the correct feature. I've got the black terminal in the COM and the red terminal where the ohm symbol is right there. And it's important to note here, whenever you're taking a measurement of resistance, pretty much all electronic equipment is going to be in parallel, so you have to isolate the resistor first. So let's just give you an example here. I've got a small, don't know if you can see that, 1K resistor. So if I pop that down and we take a measurement, should be able to see it on the dial. We've got 1.005, 1.004, so that's within 1%, as that's a 1K resistor, so that's pretty good. You can also measure things like potentiometers, and there's other things like injectors on your car. That's a good practical example actually. If you measure the resistance and it's not within a tolerance, you know the injector's bad and you need a new one. There's many other things you can do measuring resistance that come in handy. So that is just a few examples of why resistance is useful to measure. Let's now move on to our next feature. Okay, so the next feature we're going to be looking at today is the continuity symbol, which is just there. So the way in which continuity works is you basically inject a small current down the circuit, and if it's complete you'll get an audible tone. If it's not complete you won't get an audible tone, which means there's a break somewhere in the circuit. So for example, I've got a reel of wire here. If I want to inspect the cable and make sure that it's complete with no breaks in it, you basically just get your test probes, put one on each end, and you get the audible tone. It's the same for these headphones. So say I want to make sure there's no breaks in the headphones. Again, you do the same thing, pop your probes on, and you should get an audible tone, like so. And it's also a very good practical use is actually car fuses. So with car fuses, you can check them one by one, go down the line, and you should get a sound. If you don't get an audible tone, it means the fuse is probably blown and you need to replace it. So that's a very good practical use for using your continuity setting. Now just be careful when you're using the continuity setting, as sometimes it can give you a false diagnosis. So for example, if you're measuring a parallel circuit and there's a break in the cable, the current might take a different path and you'll still get an audible tone. So you want to make sure that you isolate parts of the circuit and test accordingly. Okay, so the settings that I've showed you so far in the video are some of the more popular settings you'll use on a multimeter, which was the voltage, the resistance and the continuity. So let's proceed now and take a look at some of the other settings you'll find on a multimeter. Next up we've got transistors. Now a transistor is basically a type of electronic switch. You get two types, you get NPN and you get PNP. On every transistor you'll have some writing on the front there. I don't think you'll be able to see that on camera, but if you're not sure what type of transistor you've got, if you pop them numbers into Google, it will tell you what type of transistor you've got, or if you can find a safety data sheet, even better. So to take the measurement of a transistor, you're looking for the HFE symbol. And again, you want to make sure you know what type of transistor you've got, so you put the legs of the transistor into the right holes. And all you simply do is twist the dial to the HFE symbol and you get the value just there. Now if we don't have the HFE symbol on our multimeter like this one doesn't, you can actually use the check diode symbol instead. So we'll cycle it to the correct feature and then we cycle through. We've got the check diode symbol just there, and then we can take our measurement of the transistor. So if I test the base to emitter, should get a reading of 0.727, and then the base to the collector 0.724. Now if you do have a safety data sheet, you can compare your results with the safety data sheet to ensure that your transistor is good. And it's going to be the same setting for checking diodes. So I've got a couple of diodes here. We've got a diode and an LED, which is a type of diode, and diodes only allow current to travel in one direction. So when you're testing them, you have to ensure that you test them the correct way round. If you don't, you won't get a reading. So there we've got 0.625. And here I've got a reading of 1.796. If I test the diode the wrong way round, however, you'll get no reading, it'll just come up 0L. Okay, on to the next feature. Okay, so next up we've got capacitance, which is indicated by this symbol here, farads. And if you take a look at this diagram on the bottom right, you've got the symbol for capacitance. So here I've got two capacitors. I've got an electrolytic capacitor on the right there, and on the left I've got a ceramic capacitor. And what capacitors basically do is store energy and they discharge it in the circuit when required. The capacitors have two conductors and they're separated by either a vacuum or a dielectric material. So what we'll do now is we'll go ahead and test these capacitors and see what values we get. So these are non-polarized capacitors, so it shouldn't matter which way round we take the measurement.
So we have 1.002 for the electrolytic capacitor, and for the ceramic capacitor we've got 54.87.
Okay, so let's move on to the next setting now. And finally we've got current, which is indicated by the A ampere symbol. So what we do is we get our selector dial, twist it over to the A. You've got two symbols, you've got the AC waveform and you've got the direct current underneath. And it will show you just there, DC at the moment. If you press the select button, that'll change it to AC, so you can use it for whatever application you wish. At the bottom you've got two terminals. I always like to start and put it in the 10 amp terminal, and then if it's a much smaller value you can then go down to the smaller value. That will just stop you from blowing the fuse, so it's a lot safer to start with the higher value if you're not sure. Now generally I don't like using multimeters for measuring current, and the reason for this is you have to actually splice a multimeter into the circuit, which is a lot more involved and can be quite dangerous. So I prefer using a clamp meter. All you do with the clamp meter is you clamp it over the live wire and you take your measurement. So you get your selector dial, you pop it on whatever setting is necessary, put it over the live wire. Make sure you don't put it over the live and neutral, or the electromagnetic fields will cancel each other out. and then you just take your value right there. So these are a lot safer and better to use than the multimeter. So in conclusion, multimeters are a great piece of kit. They're very versatile. You can take lots of different measurements with them. As you've seen in the video, there are a couple of applications where you're better off using other pieces of equipment, but generally they're a great piece to have in your tool bag. So thank you very much for watching, guys. Wherever you are in the world, have a great day.